You know, when you look at a massive skyscraper, have you ever wondered what's really holding it all together? It's definitely not just the concrete you see on the outside. Hidden deep inside is this incredibly complex steel skeleton. And the master plan for that skeleton? Well, it's a crucial document that you've probably never even heard of. Let's uncover it.
Right, so this intricate web of steel, we call it rebar, is where the building gets its real strength. Every single one of those bars is cut and bent to an exact specification. I mean, nothing is left to chance. So the big question is, how does a construction team take a flat blueprint and turn it into this massive three-dimensional puzzle? The answer, it turns out, is in the document we're about to explore.
So here's our game plan for this explainer. We're going to start with that hidden skeleton. Then we'll define exactly what a bar bending schedule is and why it's the key to precision. We'll look at its anatomy, see how one gets made, and finally, really understand its role as the true, unseen backbone of construction.
All right, first up, the hidden skeleton. Before we jump into the paperwork and the details, let's get a handle on why this steel framework is so fundamental to, well, pretty much every modern building.
Think about it. Modern construction is basically built on reinforced concrete. Now, concrete is amazing when you squeeze it. That's called compression. But it's actually pretty weak if you try to pull it apart. That's tension. And that's exactly where steel comes in. This internal steel skeleton, the rebar, it's designed to handle all those pulling forces, giving the whole structure its strength and durability.
Okay, so you've got this super complex steel framework on a massive construction site. How in the world do you manage all that? That brings us right to our core topic, the bar bending schedule, or as everyone calls it, the BBS. So the official definition calls it a comprehensive document with detailed information on all the reinforcement requirements. And yeah, that's accurate. It's really the official link between what the structural engineer designed and the team on the ground that has to actually build the thing.
But let me give you a much simpler way to think about it. A bar bending schedule is basically the master recipe and the step-by-step assembly guide for the entire steel skeleton. It tells you every single part you need, its exact size and shape, and exactly where it's supposed to go. No guesswork.
So why go through all this trouble? I mean, why is having this incredibly detailed recipe so important?
A single BBS solves a whole bunch of problems. First and foremost, safety. I mean, if you get the steel wrong, the building is just not safe. End of story. It also prevents a ton of material waste because you're calculating the exact amount of steel you need, no more, no less. It gives the crew on site a super clear roadmap, bridging that huge gap between the design office and the construction site. And of course, it's absolutely essential for figuring out how much the project is going to cost.
Okay, so if we were to actually crack one of these open, what would we see? Let's break down the essential pieces of the puzzle.
A BBS really stands on three main pillars. First up is bar marking. Every unique type of bar gets its own ID, kind of like a part number in a catalog. Second, you have quantities and dimensions. This tells you exactly how many of each part you need, their diameter, their grade, all of it. And third, and this is the real magic, the bending and cutting details. These are the explicit instructions. Cut this bar to this specific length, bend it at this precise angle, create a hook that's exactly this size. It's the core of the whole assembly guide. I know this might still feel a bit abstract, so let's make it, well, concrete. We're going to walk through how a schedule gets created for just one single, really common part of a building. We're going to use this simple concrete beam as our example. Now, if you look at the diagram, you can see it has different kinds of rebar doing different jobs. You've got bars running along the top, bars along the bottom, and then you have these vertical loops called stirrups that basically hold the whole thing together. So the process follows a pretty clear logic. First, you identify every unique bar in that drawing. So for us, that's the top bars, the bottom bars, and the stirrups. Second, you calculate the exact cutting length for each one, being super careful to account for any bends or hooks. Third, you count up how many of each bar type you need for the whole beam. And finally, you organize all of that data into the final schedule. And voila, this is the final product. This simple table has everything the fabrication team needs to know. For example, they can see right away they need two top bars, 12 millimeters in diameter, each one cut to 4,150 millimeters. They also need two 16-millimeter bottom bars, each cut to 4,550 millimeters. And they'll need 21 of those 8-millimeter stirrups, each cut to 1,792 millimeters before they get bent into shake. It's crystal clear, no guesswork needed at all.
So here's the really crucial point. This document is way more than just a table full of numbers. It's the vital link that makes sure what was designed on paper is exactly what gets built in reality.
The bar bending schedule is the translator. It takes the clean, perfect lines of a technical drawing and converts them into clear, actionable instructions for the messy, hands-on, complicated reality of a construction site. It's literally the bridge between the engineer's vision and the builder's craft.
So yeah, while it's probably not the most glamorous part of construction, the bar bending schedule is a true unsung hero. It's that invisible intelligence that ensures our buildings aren't just cool to look at, but are fundamentally safe, strong, and built to last.
So the next time you walk past a construction site or you look up at a finished skyscraper, maybe you'll see it just a little bit differently. Maybe you'll think about that hidden steel skeleton and the detailed, meticulous, invisible blueprint that's holding it all together.